Good morning. It is Thursday, June 4th, and today we can prepare for our circles test by practicing. So let's start by just talking about our rules, talk about everything. We'll watch our little song to help us with our big four, and we'll kind of go from there. So let's start with angles. So for angles, if we have an angle at the center of the circle, it's called a central angle, and it's equal to the intercepted arc. So if the vertex is at the center, it's equal. If the vertex is on the circle, it's half. So if this is 40, this would be 80. Inscribed angle is half of the intercepted arc. If we have an exterior angle, we have the rule 2EA equals major minus minor. And if we have an interior angle not at the center, then we have 2VA equals arc plus arc. Those are my arcs and angles rules. You also need to know that the arcs of a circle add to 360, and if there's a diameter drawn, each half is 180. Now for segments, we have wee, whole times exterior equals whole times exterior, and we have PP, part times part equals part times part. So we have our little song to help us, at least with the big four. So let's take a look at that. Again, to get to all the songs, Schlansky.com, YouTube, Common Core, so playlists, Common Core geometry songs, view full playlist, and we're talking about circle rules. So that's a little song to help you remember those big four rules. We also have arc length, we have area of a sector, we'll get to that later on. So, and then we also have our completing the square with circles. So we're going to start with that. This is the thing that we did most recently. And again, for more examples, watch the video on this. To find the center and radius, I need to start by putting the equation into center radius form. I need all the variables on one side, all the constants on the other side. So I got to move this 10 over. I'm going to write the x's together, and I'm going to write the y's together, and the constants again go on the other side. Now I'm going to complete the square for the x's. I'm going to complete the square for the y's. Oops. I like to use colors to more clearly see what's going on here. So for the x's, well, for both of them, I'm going to do b over 2 squared. For the x's, that's negative 4 over 2 squared, which is 4. And for the y's, I've got 8 over 2 squared, which is 4 squared, which is 16. Next step is to factor. It's always the same factor written twice. Whatever the first sign is, that's my sign for both. So it's x minus, x minus. And it's always the square root of that value, which in this case is 2. For the red, for the y's, they're both plus. And the square root of 16 is 4. Bring everything else down. Combine my right-hand side. The negative 4 and positive 4 happen to cancel in this case. Then I rewrite as a binomial squared, x minus 2 squared, y plus 4 squared. Now that I'm in center radius form, for the center, I negate what's in the parentheses. So positive 2, negative 4 is my center. Radius, I take the square root of the right-hand side. I get 4. And that's it. Once you do a bunch of them, it's not bad. Definitely the first example, if you're just watching this right now, you're probably lost. You have to do the lesson. Once you do a bunch of them, it's really not bad. All right. This is a pretty obscure rule. It's very simple, but when you have a quadrilateral inscribed in a circle, the opposite angles add to 180. Whenever you have a quadrilateral inscribed in a circle, the opposite angles add to 180. So KMO is 48, MON is 80. Well, the opposite angles add to 180. So 48 plus N equals 180. And these opposite angles, 80 plus K equals 180. K is 100. And is 132. That's it. So whenever you have a quadrilateral inscribed in a circle, the opposite angles add to 180. All right, looks like one of our rules now. So let's put in the information. QPS is 35. QS is 80. It's asking for RS. So for circles, you want to ask yourself segments or angles, or arcs and angles or segments. This is arcs and angles, so my two arcs and angles rules are 2VA and 2EA. Well, do I have vertical angles or an exterior angle? In this particular example, I have an exterior angle, so it's 2EA equals major minus minor. Once you have your rule, you just sub into it. The exterior angle in this case is 35. The major arc is the big arc. That's X. That's what we're trying to find. The minor arc is 80. From here, I just do the algebra. 70 equals X minus 80 plus 80 plus 80. X equals 150. Number 4, I see circles. CEB is 110. Again, I got to ask myself, am I dealing with segments or am I dealing with arcs and angles? Well, these are arcs and angles, so it's going to either be 2EA or 2VA. Are there vertical angles or exterior angles here? There are vertical angles. So it's 2VA equals arc plus arc. And now there's a little twist here. The 110 does not match up with these intercepted arcs. So to find the other pair of vertical angles, it's a linear pair, so I have to subtract from 180. So the vertical angles that intercept the arcs I'm dealing with are 70. So the vertical angle isn't 110, it's 70. Arc plus arc is 50 plus X. That's it. Blah, blah, blah. PB is 2. BC is 30. What's AP? Arcs and angles are segments. Well, these are segments that are labeled here. My two segments rules are PP and we. Is there an exterior piece? Yes, these are exterior pieces. So I'm using whole times exterior equals whole times exterior. Let's start with the secant. The whole secant is 30 plus 2, which is 32, times the exterior is 2. For the tangent, the whole is the exterior, so both the whole and the exterior are x. And that will always be the case whenever it's a tangent. I do the algebra, and x is 8. DE, let's just see if I can move this up a little bit so I can actually see it. Put it there. Perfect fit, perfect fit. Let's go blue. DE is 2x plus 8, EC is 3, AE is 4x minus 3, EB is 4. Arcs and angles are segments. Well, these are segments, so since they're segments, it's going to either be PP or we. Is there anything exterior here? No. So I'm going to be using PP equals PP. So the part times part are the two parts of the chord that's being cut. So let's start with DC. The two parts are 2x plus 8 and 3. The other chord, 4x minus 3 and 4. Notice I put it in parentheses. Whenever I'm multiplying a binomial, I should always put it in parentheses. That's an algebra thing going back to middle school. From here, I do the algebra. 6x plus 24. Make sure you're distributing. Equals 16x minus 12. I do the algebra. X is 3.6. What do we have here? I see a lot of tangents, and I know the rule that all tangents drawn from the same point must be congruent. So I'm looking here at A. I have two tangents that are both drawn from A. Therefore, they must be congruent. So if AE is 20, then AF is 20. I see, let's do a different color. Let's do yellow. I see two tangents drawn from C, so they must be the same. So this must be 24. I see two tangents drawn from B, so those must be the same. Well, little twist here, if this whole thing is 32, I could subtract the 20 to get 12, so each of those must be 12. It's asking for BC. BC is this whole thing. 12 plus 24 is 36. So the rule, all tangents drawn from the same point, is the rule that's being used in this problem. Whenever you see two tangents drawn from the same point, they must be congruent. Angle COA is 60, TA is 10. So if TA is 10, then each of those has got to be 5, and it wants the area of sector SOA. So, area of a sector. Well, we got a song for that, don't we? All right, so A equals theta pi r squared over 360. It's asking for the area of the sector. Theta is the central angle. My central angle is 60. My radius is 5 squared over 360. So now I can just go to my calculator. It wants it to the nearest hundredth, so I will type pi in. Alpha y equals enter. 60 pi 5 squared over 360 to the nearest hundredth is 13.09. So if it asks or deals with area of a sector, then you use the area of a sector formula. Now here, it's telling us that the area of the sector is 240 pi. Well, again, it's still area of a sector, so it's still A equals theta pi r squared over 360. So we're talking about sector OCD. It says that angle AOD is 80. It says that it wants OB. Well, since OB is a radius, that means that all the radii, so we're trying to find a radius. Now, this central angle is not the central angle for this sector. So this came up in the problem we did a few minutes ago. I'm going to have to subtract from 180 because it's a linear pair in the middle there to get 100. So the central angle for the sector that I'm dealing with is 100. So the area is 240 pi. Theta is 100. Radius is x. And now, since it gave me the area, I'm going to have to use algebra. I can cancel the pi's out since there's one on both sides. And now I'm going to cross multiply and solve. So 1 times 100x squared is 100x squared. 240 times 360, I don't know. 240 times 360 is 86,400. Divide both sides by 100. X squared equals 864. Square root. I go to my calculator. It wants the answer to the nearest tenth of an inch. So radical 864 is to the nearest tenth, 29.4. Oops. I don't know why it keeps on moving. What is going on here? X equals 29.4. So area of a sector, whether it's asking for area of a sector or giving you area of a sector, A equals theta pi r squared over 360. Now this one is talking about the length of the arc. Arc length is short. Again, there's so many little rules you need to know. As long as you know them, it's not bad. So S is the arc length, which in this case is 10. Theta is the central angle, which is pi over 2. R is what I'm trying to find. So from here, if I want to get x by itself, to get rid of a fraction, I multiply by 2. I get 20 equals pi x. Divide both sides by pi. I get 20 over pi. It wants the answer to the nearest tenth. So 20 divided by pi to the nearest tenth is 6.4. So you might be solving for S, you might be solving for theta, you might be solving for R. Regardless of what you're solving for, you just sub it in and do the algebra. Which brings us to our 3 special circle rules. So let's talk about our 3 special circle rules. They're all about inscribed. It's all about inscribed. I have two inscribed angles, and they both intercept this arc. Therefore, they're congruent. Angles inscribed to the same arc are congruent. If I have an angle inscribed to a semicircle, to a diameter, it's a right angle. I don't know if you can hear, my dog is freaking out right now because my family left to go on a walk without him. An angle inscribed to a semicircle is a right angle. And this one's similar to that. And I have a tangent and a diameter. They form a right angle as well because it's still intercepting an arc of 180. So a tangent and diameter intersect to form right angles. So these are your big three rules, and they're all about inscribed. For all three of these angles, you're looking on the circle, on the circle, on the circle. And by the way, in case you're wondering, same thing here. These are congruent because they both intercept this arc. So again, you're always looking on the circle, so that's something that's definitely going to help you. So let's just move this so I can actually see it. Let's just keep it here so I can use the different colors. We're going to go through each choice. We're going to see which one's not true. BUI is an inscribed angle. It intercepts arc BI. BRI is an inscribed angle. It intercepts arc BI. They intercept the same arc. They're both inscribed. Therefore, they're congruent. Choice 2. ITR and BTU. Well, they're not inscribed angles, but going back to geometry, earlier in geometry, they're vertical angles. And I know that vertical angles are congruent. So a lot of students get that one wrong because they don't have the same intercepted arc, but they're not inscribed angles, they're vertical angles, and vertical angles are always congruent. All right, two choices left. UBT is inscribed. Its intercepted arc is UR. BRI is inscribed. Its intercepted arc is BI. Do they have the same intercepted arc? No. Are those intercepted arcs necessarily congruent? No, not that I know of. So I'm going to say that one's a no. And I'm going to go through the final choice. RBU is inscribed. It intercepts RU. RIU is inscribed. It intercepts RU. They intercept the same arc. Therefore, they're congruent. Which of the following statements is not true? Choice 3. And our favorite proof. I'm always proving triangles are congruent. Is it obvious which triangles I'm proving congruent here? I'm going to go with no. I see a lot of triangles going on. So let's take a look at what they want me to prove. Statements. Reasons. MA and HT. So it looks like I have a few choices here, but it looks like those segments are in two different triangles. So this particular question, there's a lot of different ways we can go. I think the easiest way to do this, should I do it both ways? Yeah, let's do it both ways. Just because I want you to see what's going on. So it looks like I can do these triangles. Those would give me MA and HT with CP, CTC. So let's do those. And then after that, I'm going to show you a completely different way we could have done this question. So, is there anything they're giving me? No. So I gotta use my circle rules. For circle rules, look for inscribed radii diameters. Mainly inscribed. Inscribed comes the most. So do I see any inscribed angles that are in those triangles? Yes. I see M intercepts AT. I see H intercepts AT. Therefore, they're congruent. Similarly, A and T both intercept that arc. So I'm going to say that angle AMO is congruent to angle THO, and angle MAO is congruent to angle OTH. Angles inscribed to the same arc are congruent. All right, I'm done with inscribes. Radii, do I see radii? Yep, I see a lot of radii. So I can state MO is congruent to OH, AO is congruent to OT, all radii of the circle are congruent. I have more than enough information right now. In fact, I could also do vertical angles here, but I'm not going to put that in because I already have everything I need, so let's just erase that. Again, it's not wrong to do that. I just don't need it. I have enough already. So now I can state the triangles are congruent. Also, by the way, instead of saying MO is congruent to OH, you could have said MO is congruent to OT. Either way is fine. Triangle MOA is congruent to triangle HOT. Now, there's four things, but I don't have SAS based on what I marked. I do have AAS. That's the only thing that I can use here, since ASS is not one of the things that proves triangles congruent. And once I have the triangles are congruent, I can state that MA is congruent to HT, CPCTC. You know, I'm going to show you the other way. I'm not going to write the whole thing out, though. I'll just kind of mark it up. I think this way was the easiest, but I want you to understand that you have options. Oops, let's keep that. So, again, it wanted me to prove MA and HT. Well, I could prove MA is in this triangle, and HT is in this triangle. So if I prove these triangles are congruent, then I also can prove MA and HT, CP, CTC. So inscribed. Yep, I have this pair of inscribed angles here. So that's one. Now at T, I'm looking at this big one. This is an inscribed angle, and it intercepts AH, which is a semicircle, which makes it a right angle. And similarly at A, I have the same thing. This one also intercepts the semicircle. So those are congruent right angles because angles inscribed to a semicircle are congruent right angles. Any more inscribed? Yes, but they're not going to help us. I have this angle right here is inscribed to HT. This one here is inscribed to MA. Those are incongruent, so I do not know that those are necessarily congruent, so that's not going to help. Radii. Well, there are radii, but they're not going to help me because the radii are not sides of the triangles I'm trying to prove, but diameters are. So I can state that MT is congruent to AH because all diameters of a circle are congruent. They're diameters and they're also sides of the triangles I'm trying to prove. At this point, I have AAS. I'm done. Also, I could have done reflexive property over on AT since AT is in both. So you had two completely routes you could have done this. You could have gone on this question. Either one is fine. Listen, circle rules, circles unit is all about these little rules. You need to know all the little rules. We went over them. We have songs for them. You need to practice, know the little rules, because this is a take-home exam. Obviously, all your exams are take-home right now because you're home. You know, you can kind of utilize the rules. You can have them in front of you to help you instead of having to memorize them. But, you know, if you ever do take this Regents exam, you would have to have all these memorized. So again, I can prepare for my test by practicing, continue practicing, go back to any of the other lessons that I created for you. I spent a lot of time making these lessons, use them, and do well in this test, get a nice fourth quarter grade, pass the course, pass the Regents, and move on. Any questions, reach out to me and remind. I hope everybody has a great day.